Good morning, ladies and gentlemen, and welcome to the SAIEE collaborating webinar between the Power and Energy section and the SAIEE Energy Storage chapter on pump storage developments in China. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, but are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV. The registration link is in the chat box. Please register so you'll receive notifications of the uploads. The recording of this webinar will be placed under the Energy Storage chapter playlist as well as the Power and Energy section playlist on SAIEE TV. A certificate of attendance will be issued a few weeks after this webinar once we've received a CPD validation number from EXA. I'd like to introduce you to our host today, one of many hosts, Prof. Pat Naidu, who holds the position of visiting scholar in the Department of Mechanical Engineering Science and Professor of Practice in the Faculty of Engineering and the Built Environment at the University of Johannesburg. He is a registered professional engineer and a specialist consultant in electrical engineering, electrical energy, and power systems. He is a fellow of the South African Institute of Electrical Engineers, a fellow of the South African Academy of Engineers, a senior member of IEEE USA, and a member of IET UK and SEAGRAE France. Over to you, Pat.
Thank you, Mings. A good day, colleagues. Welcome, and thank you for joining us in this conversation, a joint conversation between the Academy of Science of South Africa, the South African Academy of Engineers, and our host for today, the South African Institute of Electrical Engineers. We are in conversation around electricity, security, energy storage, and as in hydroelectric pump storage. As background, the Academy of Science hosted a first webinar on hydroelectric pump storage in South Africa. The Society of South Africa has accepted electricity as the national carrier of energy to be delivered securely and reliably at the lowest cost. Now, electricity is mathematics, has to be manufactured and consumed instantly. The Academy of Science hosted the first webinar on South Africa's experience with hydroelectric power station development in balancing the electricity supply and demand on the national grid. For this webinar, we have invited the People's Republic of China to share with us their experience in developing a new power system. You'll see this emphasis on a new power system continuously during Professor Feng's presentation. In 2018, the University of Johannesburg conferred on the leadership of China, as represented by President Xi Jinping, the honorary doctorate in engineering and the built environment. This was for the sterling leadership of Chinese Politburo in terms of developing their infrastructure for national growth, development, and prosperity. And they actually moved hundreds of millions of their citizens from poverty to prosperity as based on the vision of common prosperity for all. Professor Xi Feng from the Chinese State Grid of China Technical College will present on behalf of China their experiences and plans ahead. From our first webinar, an attendee followed with great enthusiasm the conversation around pump storage and also offered to do a follow-on presentation on recommendations for South Africa. So welcome to Mr. Rubers, who will give us a view on his call for further development on hydroelectric pump storage. So thank you to the South African Institute of Electrical Engineers for hosting the Academy of Science and the South African Academy of Engineers, to the chapter chair of the Power and Energy section and the chapter chair for energy storage in particular to take forward and host this meeting. Welcome to Devekshika Maharaj, the person for the SAIEE Energy Storage Chapter. Devekshika is the Managing Director of Ikali Engineering, a multifaceted consultancy focusing on management consulting, renewable energy technologies, electrical maintenance and installation services, and training and development. She has a BSc Honours in Electrical Engineering from the University of KwaZulu-Natal. She is a professional engineer and holds several certificates in energy from the Association of Energy Engineers and the Green Building Council of South Africa. Over to Devekshika.
Thank you, Prof. To our first speaker today. It is with great pleasure that I host this in collaboration with the Power and Energy section. And this also stems off from the webinars that held last year with Prof. Ben from UWC. So I think without wasting any more time, I'd like to proceed to introduce our speaker, Mr. Zi Feng. Mr. Zi Feng is a training master at the American Association for Talent Development, as well as the director of the Power Grid Construction Training Department at the State Grid of China Technology College. He's actively involved in the development of pump storage systems in China, and his research condition-based maintenance of power transmission and distribution equipment. I'll hand over to you, Mr. Feng. Thank you.
Dr. Nadu, thank you, Mr. Devekshika Maharaj, and I'm very glad to have this opportunity to share the developments of pump storage hydropower and in new power system in China. I'll just shut down my camera for more fluency. Okay, that's me. I'm Xie Feng from State Grid of China Technology College. Now I'm a professional trainer in our college. Next slide. Next slide, please. Yeah. The topic today is the development of pump storage hydropower in new power systems. I will show you the development of PSH, the collaborative development of perspectives on PSH and the new energy storage, and will give a little discussion on the impact of a electricity price mechanism on PSH and the others. So the first slides, I'd like to brief you all the main conclusion of my presentation. First, pumped storage hydropower is a fundamental component of new power system, and it is currently becoming the most mature and cost-effective, clean, and flexible regulated power source. The construction of PSH should be considered as a whole system and should be coordinated with the development of new power storage and strengthened in diversified development. The PSH has three major functions. First, it can ensure the safety of the power grid. Second, serves the consumption of clean energy. And third, promote the optimal operation of power system. And the PSH is playing a key role in the transformation and development of clean and low carbon energy. In the early stages of energy transformation, which we are experiencing now, the development of PSH was mainly driven by policies and protected by policies, and should be gradually strengthened by market. At the same time, we should pay enough attention to PSH in reducing overall carbon emission in the power system. Next slide. Next slide, please. Next slide, please.
Sorry, Professor Feng, I think there's a lag. I'm already on the next slide, international development of PSH. Is that correct?
Yes.
Okay, it's maybe just a lag between us and you being so far away. Can you see it?
No, I'm still on the first one.
Okay.
Okay, great. This slide shows the international development of PSH. Now, more than 40 countries have set up the development goal of carbon neutralization, and many of them have made net zero promises. And now the energy transformation has been significantly accelerated. The fast developing renewable energy is leading global low carbon energy transformation. And China will play a significant role in global development of renewable energy. Even with the COVID-19, the global renewable energy have maintained a rapid growth. By the end of 2022, the total installed capacity of renewable energy have reached 3.372 billion kilowatts. And in the year of 2022, 294 million kilowatts of renewable energy had been installed, comparing with the increase of 30.47 million kilowatts in 2021. The table on the right shows the installed capacity of renewable energy from 2017 to 2022. You can see it is accelerating now. Next slide. Next slide, please. I'm still waiting.
It's showcasing China National Plan of PSH.
Yes,
do you see it?
yes. Okay, yeah, I can say it. The National Development and Reform Commission is the industry's top authorities. And in this year's, the Reform Commission published many important files. One is opinions on further improving the price formation mechanism for PSH, and the other is a medium and a long-term development plan for PSH from 2021 to 2035. In the file, it is listed the target of the development is giving out, which means by the end of the 14th five-year plan, which is 2025, the total installed capacity of PSH will be 62 million kilowatts, and by the end of 2030, which means the end of 15th five-year plan, the total installed capacity of PSH should be around 120 million kilowatts. And in China now, there has been a broad consensus among all sectors of society on the importance of PSH in building a new power system and on further accelerating the development of PSH. The attention and the participation in PSH have also shown an unprecedented new surge. Next slide. Okay, okay. My presentation have 4 parts. 1, 2, 3, 4. Next slide. Today, we are talking on the topic of strengthening the leading role of new power systems in development of PSH and the collaborative development of PSH. Okay, The first part strengthens the leading role of new power system in the development of PSH. Next slide.
Professor Feng, we have page 11 showing on the screen. Do you see it?
Yes, I've seen it. Thank you. And since we are talking about the new type power system, and a new power system has the characteristics of high proportion of renewable energy and a high proportion of power electronic devices. So building a new power system is a complex and systematic project, requires a simultaneous consideration of the three aspects. We must consider the power safety and stability, continuously increasing proportion of new energy, and a reasonable system cost. And it is very necessary to handle the relationship between clean transformation of thermal power units, orderly increase the renewable energy such as wind and solar, and the construction of power grid coordination and mutual assistance capabilities, also the reasonable allocation of flexible resources. The scientific planning of the construction path is a foundation, boundary, and guide for development of various entities in the new power system. So there are many factors for us to consider. Next slide.
Sorry, Chair, if I can just quickly come in to assist. So, Prof, when you say next slide, you must just be aware that everyone else is on the next slide. So you can talk through it as though you can say it. So I think that's going to help. If you do have it print out of you, just tell us what's the title of the next slide, and Mings will have it on. Thanks.
Okay. This slide shows the brief situations of thermal power in China. By the end of 2021, the installed capacity of thermal power has exceeded 1.1 billion kilowatts, and the total capacity accounting for 46% of the total installed capacity of 2.378 billion kilowatts. And the thermal power generation is 5,000 billion kilowatt hour, accounting for 60% of the total power generation capacity. And the carbon dioxide emission in the thermal power generation accounts for about 40% of the 10.3 billion tons of power production. So now in China, we still have a large capacity of thermal powers, around 46%. It's a long way to transformation. Next slide. Okay, this slide shows the development of renewable energy in China. By the end of 2021, the installed capacity of wind and solar power is 635 million kilowatts, accounting for only 11.14% of the total possible capacity of 5.7 billion kilowatts. The power generation of renewable energy is 982.8 billion kilowatt hour, accounting for only 11.7% of the total power generation. So there's still a serious lack of flexibility resources in the system. And the installed capacity of flexible regulating power source, such as pump storage and gas power generation, is 145 million kilowatts, accounting for 6.1% of the total installed capacity. And there is still huge room for improvement in installed capacity and power generation, especially as a green and clean flexible regulating power source. PSH has an installed capacity of 45 million kilowatts accounting for only 1.53% of the total installed capacity, far behind the level of 4% to 8% in developed countries, such as Europe and Japan. So efforts still need to be made to accelerate the development and construction. Next slide. Okay, I have mentioned that in this years, the Chinese government have published a series of important files, including the medium and long-term development plan for pump storage hydropower from 2021 to 2035, medium and long-term development plan for hydro energy industry 2021 to 2035, and the 14th five-year plan for renewable energy development. The 14th five-year plan is the year from 2021 to 2025. So we can see that the China government has a long plan. No. The previous slide, please. Has a long plan for the future development. And it is very necessary to strengthen the planning guidance and fully consider the connection between the PSH owns development and the construction needs of the new power system. Okay, this slide is okay. This slide shows the development of PSH in China. And by the end of 2022, China's installed capacity of PSH was 45.79 million kilowatts, and through the construction of a number of large-scale PSH, a whole industrial chain development system and a professional development mode are formed, covering standard, planning and design, engineering, construction, equipment manufacturing, and operation and maintenance. Next slide. This slide shows the advantages of PSH in many scenarios. PSH can greatly support the system security and is an economical green energy storage and can provide a flexible adjustment of power supply. Other comprehensive advantages include it can improve the efficiency of conventional power. It is a reliable means of system stability control, and it can provide system balance support, etc. Yes. It can also promote the effective grid connection of distributed generation. It can guarantee the low carbon economy of the system and improve the quality of power supply on the other side. So next slide. In building new power system, there are other measures to increase the system flexibility. These measures include the output prediction of new energy, demand management on the load side, and the flexibility transformation of the thermal power units. So in this and also virtual power plants, etc. So in this situation, the cooperated development of various entities, the optimized allocation of resources, and the saving of economic costs. These factors are all need to be coordinated on a larger scale and a longer term scale. So, and the scientific and reasonable planning should be formulated. Next slide. Now we are going to talk about the collaborative development of PSH and new energy storage. With the high infiltration of new energy sources such as wind and solar in new power systems, it is necessary to allocate a certain proportion of energy storage to ensure the safe and stable operation of the power system in order to address the issues such as discontinuous and unstable output of new energy. And now the total installed capacity of wind power and photovoltaic in China will reach over 1.2 gigakilowatts by 2030. Based on the estimated 15% allocation of energy storage capacity, it is estimated that at least here is a little, at least 180 million kilowatts of energy storage needs to be matched. At present, the development scale of new energy storage and PSH is relatively lagging behind. At the end of 2021, China has put into operation 5.73 gigawatts of new energy storage, and the installed capacity of pumped storage is 45 gigawatts. So now it is necessary to work together and coordinate the development in the future to meet the regulatory needs of the power system. Next slide. Okay. The new type energy storage, there are many types of, include the electrochemical, flying wheel, compressed air, hydrogen energy storage, etc. And most of this new energy storage technologies have the advantages of short construction cycles and simple and flexible site selection. But now the current economic efficiency is not ideal. Next slide. Here are three examples. First, the electrochemical energy storage. The scale of electrochemical storage is usually in the range of 10 to 100 megawatts, with response speed ranging from tens to hundreds of milliseconds. It has high energy density and good regulation accuracy. And the second, the electrochemical energy storage is mainly suitable for distributed peak shaving application scenarios. It is usually connected to the medium and low voltage distribution network or new energy field station side. The compressed air energy storage uses air as a medium and has the characteristics of large capacity, multiple charging and discharging times, and a long service life. Now, the compressed air, its current efficiency is relatively low, but now it is the most similar energy storage technology to pumped storage for areas such as deserts and Gobi deserts that are not suitable for PSH. Compressed air storage can effectively cooperate with the consumption of renewable energy in large wind farm and solar bases. And third example is hydrogen energy. Hydrogen energy has the characteristics of large-scale and long-term energy storage, which can promote the optimal allocation of heterogeneous energy across regions and seasons. Next slide. This picture is Mr. Shu Yinbiao. He is the chairman of IEC, and he is also the former president of SGCC. On the latest New Power Energy Forum, Mr. Shu Yinbiao gave out the 5 requirements for new type energy storage. The first one is it should provide reliability and safety. As a crucial component of the new power system, energy storage must ensure its own safety, which is a fundamental prerequisite. Along with the increase in energy density and the expansion of capacity, especially after being widely deployed in cities and entering thousands of households, there are more demands placed on the safety and reliability of energy storage equipment. The second one is superior performance is required. Energy storage, next slide please, on Mr. Shu Yinbiao's, yes. Energy storage must exhibit excellent performance within the power system, with the characteristics such as long cycle life, high conversion efficiency, and low capacity decay. It must ensure a safe, economical, and efficient operation to meet the needs of various market-oriented scenarios within the system. The third aspect is to achieve flexibility and intelligence. By leveraging digitalization, energy storage should enable real-time equipment monitoring, safety early warnings, and intelligent maintenance, allowing for flexible and efficient interaction between the power generation sources, the grid, loads, and storage. The fourth one is the environmental friendliness should be achieved. It is essential to enhance the high quality recycling and utilization of renewable sources, reduce the carbon footprint throughout the product's life cycle, and provide more green value to the new power system. The last one is new type energy storage should provide active support to the power grid. Energy storage must be capable of addressing the intermittency and the variability of new energy sources, especially the long-term regulation requirements of more than 6 to 10 hours posed by the large-scale integration of photovoltaic power into the grid. Next slide. Comparing with the new type storage pumps, the PSH have the advantages of high technological maturity. It experienced the development of 114 years, and the PSH can have very large capacity. Generally, a PS station could have 1.2 to 3.6 million kilowatts, and it has a long lifespan, at least 40 years, usually to 60 years. And also it has high reliability and cost effectiveness. PSH is especially suitable for scenarios with high demand for peak shaving capacity of electricity. And it is usually connected to the main network, to the main grid at a high voltage level. In China, it's about 202 kilowatts and 500 kilowatts. So considering the diverse regulatory needs of the new power system, the diversified development of PSH should be taken seriously. Next slide. There are many ways for the multiplied diversified development of PSH. One way is to strengthen the development of small and medium-sized PSH. Such PSHs have the advantages of abundant site resources, a flexible layout, and usually close proximity to load centers, and can provide close integration with a distributed new energy. And the second one is to develop hybrid pump storage power stations according to local conditions. And China has a high level of conventional hydropower development and abundant station resources. The picture on the down left is the Shanxi Ankang hybrid pump storage power station, and the picture on the down right is Sichuan Yalong River hybrid pump storage power station. So by using suitable hydropower station sites and adding reversible units to develop hybrid pump storage power stations, the construction cycle can be shortened and the existing infrastructure can be utilized and the construction cost can be saved. The hybrid pump storage power station uses conventional reservoirs for upper and lower, with a large regulating capacity and a long continuous power generation or pumping operation time. It can be adjusted weekly or quarterly. Next slide. The third way for the diversified development of PSH is to explore the development and application of seawater PSH. For seawater PSH, there's only necessary to build upper reservoir. The large-scale grid connection and consumption of offshore wind power requires the allocation of corresponding flexible adjustment regulation resources. The seawater PSH resources in the coastal areas in China, according to our investigation, is around 42 gigawatts, which has good development prospects. And now, the first seawater PSH trial unit is under construction. It is located on Buying Island, Xiapu County, Fujian Province. Its installed capacity is 42 megawatts. Next slide. The third topic is the impact of electricity price mechanism on PSH. Actually, in China, we experienced the three phases of development of electricity price mechanism on PSH. PSH serves the entire power system, including the power sources, power grids, and users, and all parties can benefit from the non-competitive and non-exclusive characteristics. So from an economic perspective, the products provided by PSH belong to the public goods and can provide public services for the efficient operation of the power system. Prior to the reform of the power system, that's around 2016, the state issued policies clarify that PSH mainly serves the power grid and is mainly operated or leased by the power grid operating enterprises. It means that all the installed capacity of all the PSH, the costs are undertaken by the state grid. Next slide. The second phase, after the reform of transmission and distribution electricity prices in 2019, the file, the notice of the National Development and Reform Commission, the top authorities, on improving the price formation mechanism of pumped storage power stations were released. This file specified that a two-part electricity price system will be implemented, and it will be determined based on the principle of reasonable cost plus allowable return. The capacity electricity tariff and the pumping losses of pumped storage power stations are included in the unified accounting of local, provincial, or regional power grid operating costs and are considered as factors for adjusting sales electricity prices. Next slide. The third phase. In May 2021, the National Development and Reform Commission released a new file, which is the opinions on further improving the price formation mechanism for PSH. In this file, the policy scientifically defines the pricing policy for PSH. The capacity electricity price was determined using the operating period pricing method, which is around 40 years and recovered through transmission and distribution electricity prices. In conjunction with the pieces of electricity market reform, we have explored the spot market for electricity pricing. The introduction of the policies has effectively stimulated the investment willingness of social entities, laying a solid foundation for the rapid development of PSH. I've just mentioned that now the price of PSH is a two-part electricity price system. The capacity price and the energy price. In areas which has carried out the spot market, the pump price and the generation price are decided by the real-time price of the spot market. But in areas which haven't not carry out the spot market policy, the power generation price should be decided by the benchmark price of thermal power, and the pump price is the 75% of the benchmark price of the thermal power. Next slide. With the full development of renewable energy and its gradual becoming the main power supply entity, the construction of China's electricity market is also constantly improving and maturing. The flexible regulation resources will become the main demand in the new power system, and the supply of pumped storage and new energy storage entities will also be more sufficient. At that time, the construction of renewable energy and flexible regulation resources will be mainly driven by market forces. So the price mechanism of pumped storage and the other entities will truly reflect the market supply and demand relationship, reflecting the full competitiveness. Next slide. We'll talk a little about the PSH in reduction of carbon emission. In traditional power system, the role of PSH is mainly reflected in the reduction of carbon emission is reflected in two aspects. First, it can replace the thermal power for peak shaving in the system, thus reducing the starts and stops of thermal power units, and reducing the load fluctuation of thermal power units. The second aspect is that PSH can leverage the safety and stability supports of frequency modulation, phase modulation, rotating backup, and emergency backup, as well as to replace thermal power units for emergency backup, thus increasing the output of all thermal power units in the system. Next slide. And in the new power system, the role of PSH is nearly the same as in traditional power system. On one hand, it plays a role in peak shaving to assist the consumption of new energy in large grid. On the other hand, it is also to leverage the safety and stability support of frequency modulation, phase modulation, and rotational backup to help the system overcome the unstable output, thus further increasing the infiltration of new energy in the power system and reducing carbon emissions. Next slide. Even the PSH and the new energy storage is developing very fast in China. Now, still we are facing some challenges. The first one is the mismatch between planning and actual demand. The current planning for PSH often fails to fully consider the specific needs of power system, such as peak valley load characteristics and the penetration rate of new energy and the regulatory capacity of the power grid, thus leading to an irrational source allocation and projects that do not align with actual needs. The second is the economic viability and cost-benefit issues. PSH face high construction and operation costs, and there is uncertainty whether the capacity electricity prices of later projects can cover the total cost, thus affecting the economic viability and investment returns of the project. The third one is the environmental impact and the sustainability. The construction of pump storage hydropower may have an impact on ecosystem, including water resource utilization, changes in land use, and biodiversity protection, and must comply with environmental sustainability policy standards. The fourth is the technical challenges and innovation needs. The current level of technology limits the efficiency and economic viability of pumped storage, necessitating breakthroughs in key technologies such as high efficiency units and intelligence maintenance technologies. The fifth one is incomplete market mechanism. Even though we have published a series of files, there's still incomplete. The market access restrictions, non-transparent pricing mechanisms, and lack of competition affect the economic viability of PSH, necessitating a sound market mechanism to enhance their competitiveness. And the sixth one is the recognition and accounting for carbon reduction benefits. The role of PSH in carbon reduction is yet not fully recognized, and that there is still a lack of quantitative assessment and policy support affecting the positioning in the power system. So next slide. 2024 is the fourth year of our 14th five-year plan. By the end of 2025, we have some goals to achieve. One is that we'd like to realize a giant leap of skill of construction. During the 15th five-year plan, the number of projects will exceed 200, and the skill and the construction will be 100 gigawatts. And we'll have wider application scenarios for PSH. The integration of cool, water, wind, and storage are gradually forming. Also, the diverse features is basically formed. In addition to State Grid Xinyuan and China's Southern Power Grid, Three Gorges Corporation, that's big companies in China, China Energy Group, State Power Investment Corporation, Jiangsu Guoxi, and Huayuan Power has become new investment entities. And also other construction companies such as CSCC, CRCC, and RECG will join the traditional power construction teams. And the industrial system will be even perfect. The integrity of industrial chain is will be further improved. The patterning and the coordination within the industrial chain will be even smooth. The supporting capabilities of the industry are significantly enhanced, and the application of new technologies and products will be faster. The industrialization of the pumped storage industry and tourism will be gradually strengthened, and a number of special tourism projects centering on the pumped PSH will gradually emerge. Next slide. To wrap up today's discussion, we mainly focus on how to meet the flexibility demands of new type power systems. In constructing new power systems, enhancing flexibility involves efforts across all aspects of the electricity system, including generation, transmission, distribution, storage, and consumption. Technologies such as PSH, advanced battery, electrochemistry storage, coal-fired power plants, gas-fired power plants, and water power plants, or V2G, the technology of V2G, each have their suitable application scenarios. So when devising plans, it is crucial to consider the overall system cost and the market conditions and conduct a comprehensive techno-economic comparison of various resources. Additionally, the integration and development of renewable energy sources must be adapted to local conditions. The development and construction pace and scale of pumped PSH must take into account the operational needs of the power system, cost effectiveness, the environmental protection, to avoid overdevelopment and resource wastage, thus ensuring that the development of pumped PSH aligns harmoniously with the broader energy system and social economic growth. Okay, that's all for my presentation. Hope you like it. Thank you very much.
Thank you, Mr. Feng, and apologies for the delay on our end with the slides. I think Minx came to doing a pretty good job. Before we continue with the program, I'm just going to do a little bit of SAIEE marketing. On the right-hand side of the screen, there is a drop-down menu called Handouts. I am supposed to inform all our attendees that you can definitely download these. One is the 2024 Training Academy brochure, where all our training courses are highlighted for the year. And the second is the main issue of the What Now journal that's published on a monthly basis. So it's under the drop-down menu called Handouts. Okay. Thanks, Prof. Feng. I think that was a very informative presentation. I look forward to the panel discussion on the various parts. And I think what's important there is the implementation of the solutions that you mentioned with regard to local conditions. And on that note, I'd like to just mention our next speaker, who is Etienne Rabers. He is the managing partner of Renewable. He is a conceptual thinker with 25 years of experience in the energy / financier with extensive experience in the renewable energy, gas and electricity sector, business, technology, and finance interfaces. He's passionate about energy transition, energy security, and the decarbonization of the economy. Etienne, if you're ready to go, I'm going to hand over to you. Great.
Sorry. Hello, can everyone hear me?
Yes, we hear you.
Great, thanks. My presentation is really to discuss from a South African perspective, what do we need to do here to have the right power systems. So what is clear, and I think was highlighted by the previous speaker, that we'll need additional storage as we have additional renewable energy. Now there's a few storage technologies you can use. One is the battery storage, which has an important role to play, particularly with ancillary services, but it's ideal for short-term storage and the decentralization of the power system. Pump storage, on the other hand, has a very important role for large-scale storage, and it's important to mitigate the seasonal variations in electricity supply and demand. Now, the disadvantage of pump storage is that they've got a long implementation time. Our last pump storage project in Gulala took 11 years to implement, and these projects are large and lumpy. In China, the implementation of pump storage projects are a lot quicker. Maybe the previous speaker will be able to discuss how much shorter it is, but it's less than half of what it took to take Ngulala to completion. The disadvantage of pump storage is you must locate it where the topography is suitable, and that might not be the best location to support the grid. So what is clear is we'll need both pump storage and battery storage. And there's also other storage technologies which are being developed or which are in operations, like thermal storage, which is used for the CSPs, where they use molten salt storage. But I think what's key for South Africa is that we focus on proven commercialized technologies. We need to be careful and steer away from trying to develop technologies that are not proven, given the limited resources, both intellectual resources and financial resources. Now, investing in pump storage is really a no-regret investment, because what is clear is you'll need additional storage in the future. Pump storage has a long economic life. It's more than 50 years. And the nice thing is they don't degrade with time. So for instance, batteries, they degrade with time and they only have a life of 10 years. But pump storage has an extended life. So the recommendations that we have is it needs to be a final investment decision on a pump storage project. And the Tubatsi project is the most likely project to reach FID first. Much of the work has been done on Tubatsi. It was only shelved in 2008 because of the global financial crisis. And Ngulala was selected to go ahead of Tubatsi. There have been announcements that Tubatsi will start construction in 2027 and be completed by 2033. But FID has not been taken, but at least development work is being done. The second point for the recommendation is we need to do preliminary development work for 2 or 3 additional sites. And the cost of that preliminary work should not be prohibitive, but it's really a pre-investment that will give us optionality and reduce the implementation time for future projects. What takes a lot of time for pump storage projects is really the permitting and the EIAs and the preliminary designs. And if we can cut that out, it will help us to roll out pump storage. The third point is the long-term strategic plans that we have. In China, there's always a good 50-year plan or long-term plan. And so they plan the economies based on the long term. In terms of the IRP, we only have a 10-year plan. And because it's only 10 years, pump storage projects are not favored because they have long implementation times and long economic lives. So the recommendation would be to have a long-term strategic plan as part of the IRPs. Now, the question is, how do we ensure that these recommendations are implemented? And any suggestions from the team would be very gratefully received. Right, just as background, utility scale storage is important to provide stability for the grid, provide ancillary services, and also give you black start capabilities. Also, storage will allow you to make best use of the generation assets and avoid curtailment. And I think it was discussed by the previous speaker in that your thermal plants will be able to run at more stable conditions at a steady state, and your PV and solar and wind projects would avoid curtailment in that you would have storage to store the electricity when you don't have enough demand. Currently, we've got 2,700 megawatts of pump storage. And we plan to have 1,231 megawatts of battery storage. But we also have more battery storage behind the meter, because as you know, with the load shedding, a lot of businesses and homes have installed batteries behind the fence. The storage will become more important as the renewable energy penetration increases. Now, there's a misconception that there's a limited number of pump storage sites that we could use in the country, but there are a lot of sites, and there were more than 90 sites identified by Eskom in the early 2000s. Another misconception, which is not in the slide, is that pump storage requires a lot of water or consumes a lot of water. because we lump pump storage with hydro. Now that's inappropriate. Pump storage does not use water. It really just pumps the water up and down the hill. And all the water you lose is evaporative losses and losses through geological faults. And I think that's important to note, because pump storage is suitable for an arid country like South Africa. And South Africa has the right topography for pump storage. The costs of pump storage are very site-specific. It depends on the geology, for instance, but it is the most cost-effective solution for large-scale storage. Next slide, please. Thanks. We did some stochastic modeling of the past system, taking into account the profiles of South Africa's electricity supply and demand. And we looked at 3 dates, 2030, 2040, and 2050. And based on those dates, we looked at, well, how much storage does our power system need? So you'll see in the 3rd column, you have the amount of thermal, or amount of coal that we have in our fleet. And as you can see, it reduces with time as the coal fleet retires and as you try to decarbonize the economy. On the extreme right-hand side, I express how many ingulanas we need or what storage we need, expressed as the number of ingulanas. And as you see, by 2030, we already need 2 or 3 ingulanas. That increases with time going forward. But what's important to note is, as you reduce your thermal portion in the electricity mix, and you have more and more renewables, the amount of storage increases exponentially, or the amount of storage you require increases exponentially. And you'll see that in the 3rd column, your coal percentage goes from 85 to 60%, then 30%, then 20%. But the number of ingulanas you need increases linearly, while the decrease in coal fleet reduces by a smaller amount. Now, the analysis we did took into account the stochastic modeling based on the average solar and wind output over a year, and does not take into account the seasonal or daily variations. So the amount of ingulanas which I've quoted here are actually on the low side. It will likely be bigger amounts in reality. So these are minimum numbers. Can you have the next slide, please? Right, I'm not going to go through this slide. It's really an illustration of the stochastic modeling we did. Looking at the gray is the thermal plants, the blue is the wind, and the yellow is the solar. And as you go from left to right, your gray bars decrease because you displace your thermal, and your wind and your solar increases. And from that, we determine how much additional storage we need. Going to go to the next slide, please. If we're going to miss the next 2 slides, I think. This was really just details of how we did the stochastic modeling. We can discuss outside the session, but I'm just conscious of time. Next slide, please. Right, if we look at the pump storage capacities that we have in other jurisdictions, in places like Switzerland, Austria, and Portugal, you have pump storage penetrations of between 18 and 33%. So they're pretty high there. In South Africa, we've only got a 6% penetration. In countries like China and the US, they've got relatively low penetrations, but it's partially because China has a lot of hydropower, which can mimic the characteristics of pump storage. And in the case of the US, there's a large number of gas-fired plants, which, unlike coal, are good. They're good for load following. Now, South Africa, in the future power system, we will need more storage than most countries around the world. This is because we've got better renewables resources, so we should have higher penetration of renewables in the long term. And the second thing is our demand is skewed to the residential market. And so we have bigger morning and evening peaks, so that will mean that you need additional storage. Next slide, please. Right. As I said earlier, Eskom looked at 90 sites in the early 2000s. They narrowed it down to 5, and eventually Ngulala was selected as the preferred site. The other sites are listed on the table just below that. And before the selection of Ngulala, the feasibility studies of 5 sites was done. But in the case of Tubatsi, that was approved by the board in 2008. It was put on hold because of the global financial crisis. But we need more than two facilities with a capacity similar to Ngulala by 2030. But unfortunately, we're not going to be able to achieve that, which means we will need to run our peakers at a larger capacity than optimal, which is bad for decarbonization. But unfortunately, that's where we find ourselves. Pump storage is a no-regret investment. I think, yeah, they're going to degrade with time. They've got long economic lives, and yeah, we will need them in the future. Eskom and South Africa needs to work tirelessly because pump storage projects have long lead times, and even if it's sanctioned right now, if you base it on the Ngulala project, it will only be in operation in 2035. Which is not optimal for the country. So it's suggested that, or recommended that Eskom expedites its investments in additional pump storage facilities. Next slide, please. Right, I've got 2 slides. I'm just comparing pump storage to battery storage systems. If I can just summarize some of the key points. Pump storage has orders of magnitude more storage capacity than battery storage. If we compare Ngulala to the largest battery facility in the world, it's 18 times bigger. And Ngulala is not the biggest pump storage facility in the world, but it just shows how much bigger pump storage can be than battery systems. Unfortunately, pump storage has a long lead time. Battery storage, you can have it up and running within 18 to 24 months. There's construction risks with pump storage in that it's dependent on the site and the geological conditions. And it's really difficult to quantify the geological risks until you've really started excavation. So there's a risk component of, well, how much will it actually cost? In the case of batteries, it's limited construction risk because they're mass produced in a workshop and in a controlled environment. Next point, pump storage projects are large and lumpy, and the location is determined by the topography, while battery storage are small and you can locate it where it best supports the grid. A key aspect is the construction materials. In the case of pump storage, you really need cement, aggregate, and steel, which are locally available. Well, in the case of batteries, it would use lithium, nickel, graphite, and other materials which are largely used for electric vehicles. Electric vehicles are able to afford higher prices for those materials. So the availability of those materials for utility scale projects is questionable. Building a pump storage facility in South Africa will use South African labor, which is important given our high unemployment rates. While in the case of a base facility, you would really import the base system from offshore. And really the only labor you require is the balance of plants and the connection of the containers to the grid. Thanks. Next slide. As I mentioned before, the economic lives of the projects are quite different, and also the degradation of the performance of the projects. In the case of batteries, they only last 10 years and they degrade over time, approximately by 1% per year. Pump storage can give all the ancillary services and can stabilize the grid, but it's got a slightly slower response time than both batteries and thermal options. Batteries are far better to provide those ancillary services, given that the response times are faster. Plus, you can put batteries where it supports the grid, while you can't do that with pump storage. Pump storage is ideal for long-term storage, while battery storage is rather short-term storage for intraday variations. The round-trip efficiencies of pump storage is slightly lower than battery storage, so that's a downside of pump storage. Pump storage has fewer environmental impacts than traditional hydropower, and often people hear the word pump storage hydropower or pump storage hydro. They link the two, but it's very different, and we need to make sure people move away from that mindset. Now, South Africa is an arid country, and many people say, well, because pump storage will need water, it's not suitable for an arid country. But pump storage really uses a lot less water than people believe. All you actually do is pump the water up and down the mountains, and all you really use is surface evaporation and water through geological faults. The last point is pump storage can give you valuable co-benefits like security of water supply, irrigation, and flood control. Thanks. Next slide. The point here is really that pump storage has not been in the IRP since 2010. And the reason for that is really the IRP only looks at a 10-year window. And so to be able to justify a pump storage project, it's basically impossible, because the plant will only be up and running in the 7th year of, or in the case of Mgalala, it will start up and running 10 years just outside the timeline of the IRP. In the case of BESS, given that they've got a short construction time, it appears quite easily within the IRP. So the recommendation here is that South Africa needs to have a long-term view and not limit ourselves to just 10 years. And I think it's a failing, often in Africa and South Africa, of really being myopic and really looking for tomorrow and not the long term. And that's where I think we need to learn from the Chinese systems, where they really look at a 50-year view, and they're reaping the benefits of that. Next slide, please. Right, just to repeat the recommendations which I had at the beginning of the presentation. It's really, we need to do a final investment decision on a pump storage project. There's talk that Tubatsi is going ahead. It will start in 2027 and be completed in 2033. But that construction time is less than what it took for Ngulala, so it's optimistic. But we really need to use every efforts to be able to start construction of Tubatsi before 2027. And once we start construction, to have it completed before 2033. We need to do development work on 2 or 3 additional sites and do the long lead items like permitting and the preliminary designs. And then, as I repeated previously, we need a long-term strategic plan. I think the key question and the key insights I'd like to get from the attendees is, how do we get these recommendations implemented? And South Africa needs this, and my concern is we have an electricity crisis, and given that people are really thinking short term, you're thinking of, well, is there going to be load shedding tomorrow, instead of having standing back and having a longer term view. With the restructuring of South Africa's electricity systems and the separation of transmission, it's really an ideal opportunity to take the right steps now, so that we get on the right path. Thank you.
Devaksha, are you with us? I think Devaksha might have technical issues. I'd like to introduce you to the chairman of the SAIEE Power and Energy section, Mr. Mondi Soni. He is also leading a few working groups focused on distribution, network planning and analysis. Mondi is an elected member of the Council for South African Institute of Electrical Engineers, a voluntary contribution position he has held since 2017. He was awarded the Engineer of the Year award in 2019, which is one of the SAAE awards, and an achievement he holds close to his heart. Over to you, Mondi.
Thank you. Thanks, Minx, and good afternoon, colleagues. And really, thanks for. Sorry, Minx. Let me just get an indication. Can you hear me?
Yes, I can. Please proceed.
Okay, thank you. Thanks to the 2 presenters, the main presentation and Etienne. And so now we are going to go through the questions and answers session. And maybe before that, I have noted some of the questions on the chat box. We will pay attention to that, and more questions are still welcome. So I think firstly, I just want to recognize that the SAIEE president is also in attendance, Mr. Pascal Mzosele. So I don't know, Minx, at the end, if he can also just do the closing remarks. We didn't know that he would surprise us. Maybe he just wanted to check what we get up to. So if you can make him give him right at the end to actually say a few words in closing. So with that being out of the way, I'm the chair of the SAIEE PES, or Power and Energy section. We appreciate what the energy storage chapter has done, collaborating and also from our side providing the support that is necessary to make this event possible. So without any further ado, let me just get into the questions. So I think just taking from the last presentation that we had now, let me just apologize. My video I cannot show because my computer for some reason decided to not to allow videos, you know, the webcam. So just taking from the last presentation from Etienne, I think this goes to everyone who is in the panel here. It looks like there is less interest on, and I would say especially locally in South Africa, there's less interest on pumped storage as compared to battery energy storage systems. And I noted what the last presenter mentioned, that, you know, the IRP is 10 years, and, you know, the turnaround time for hydro is much longer. But is that really the case? So the IRP is has got those kind of shortfalls, and that's why there is less interest. And I would like also, you know, in the answer or in the responses, anyone please touch on small scale hydros as well. We have seen some of them in the Eastern Cape area. Some are no longer in operation. But then again, why does it look like there is less interest on this storage technology than others? I will start with past President Andres Mtetwa. I know you are also able to speak out. If you can please just take a bite on that.
Thank you. Thank you, Chair. Yeah, good afternoon, everyone. It's great to listen to the international presentation from China, as well as the local presentation from Mr. Rubbers, and I think it carries a lot of lessons for us going forward. Indeed, the draft IRP, as we see it at the moment, has no provision for PSH, and I can't understand that, because that has happened before. Previous IRPs in the past I think did make provision for this. So I don't understand why there's no provision at the moment, which goes back to what the chairman of the Power and Energy section is referring to in terms of interest from the powers that be. And then also, just to comment on the mini hydros, as you're saying, I know this is not a mini hydro webinar. There is definitely an issue around that, in the sense that I'm not sure how many mini hydro stations have been provided in terms of Lesotho Highlands Phase 2, for example. I'm aware of Phase 1, where we have the Bethlehem Hydro. Those are small hydros. One is 3 megawatt, the other one 4 megawatt. They have a power purchase agreement with the Council of Bethlehem. And I don't know, on our side, on the side of South Africa, as the water flows down to the Vaal River or the Vaal Dam, why don't we build some more mini hydros there? So especially the opportunity now would present itself with Lesotho Highlands too. So that's my take at this stage, Chairman. Thanks.
Thanks, Past President. Etienne, do you want to just respond to that as well?
No, I'm in full support. I agree with what you said.
Okay, all right. So thanks, Etienne. So I think it's perhaps we do need to have this conversation as well going forward. But then going back to the perspective from China, yeah, I saw Mr. Feng. I saw some really good numbers that were shown there. And maybe let me just take a question. The first question that was asked by Walter Moilwa was, have you ever taken other types of additional energy storage, such as gravity buoyant battery systems, most applicable in dams or pumped storages? That's the question meant for Mr. Feng. Thanks, Walter. Mr. Feng?
Yeah, but I'm afraid I didn't catch you. Would you please type your question in the chat box?
Okay, I'm sure you can see the questions tab on the go to webinar menu.
No.
You can just click on that questions tab. The first question there from Walter.
Sorry, Professor Feng, you cannot see the questions. If you can hear me, the question is, have you ever taken other types of additional energy storage, such as gravity buoyancy battery system, most applicable to dams or pumped storage?
I beg your pardon.
Sorry.
Would you please repeat the question?
I'm going to ask him slower.
Yeah.
Sorry, Mondi.
Yeah, I wanted to say maybe we can go past this question and we can then submit it to Mr. Feng at a later stage if that is fine.
No problem.
Is that okay?
Okay.
So I think the question that kept on coming to mind during the presentation on the Chinese perspective is what kind of and I was carefully looking at the numbers that we have there. What kind of LCOEs or levelized cost of energy are we looking at in those developments in China? And perhaps also, Etienne, if you have our own perspective as well, you can also just comment on that. But I would like to know from the Chinese side, and then we compare to what you have. China levelized cost of energy, PSH? Question mark. Okay. I hope colleagues means you can hear me. I don't know.
Can I maybe just comment on that?
Yes, please. Yeah, go ahead. Yeah.
We'll not really have a levelized cost of electricity. It doesn't. So I'm not sure what you mean by that. Just the cost of storing a megawatt.
Okay. The LCOE basically meaning that the total cost of bringing a plant to life and operating it over its economic life, that now compared to what it gives you in a form of energy. So it would come in a form of rands per kilowatt hour.
But it will all depend on how hard you use your pump storage. Because if you fill it and you empty it every day, you'll have a very different cost than if you only do it seasonally and once a year.
Okay, thanks, Etienne. And I think Neville also wanted to know the same thing. So the question was, what is the cost per kilowatt hour for pump storage versus battery energy storage. So I think in your comparison, there was, that kind of question mark that maybe if we can compare the rand per kilowatt hour for the two. And do you want to also take that?
Yeah, regarding the rand per kilo or rand construction costs, in the case of a pump storage project, it's very dependent on the geology and the site-specific nature of the plant. But what is clear is for large-scale storage, batteries are not suitable. The biggest batteries in the world are 18 times smaller than Nkulala. You will need pump storage for interseasonal balancing of the electricity demand. So it's not fair it's not fair to compare pump storage to batteries because they each have their role to play in the power system. But yeah, so pump storage is far better for long-term storage. Batteries are far better for ancillary services and short-term fluctuations in the grid. So for instance, if you have a PV plant, it makes a lot of sense to co-locate a battery system on that plant so that you charge the battery during the day, or at midday you charge the battery, and so you can discharge it at night so that you have a constant release or availability of power.
Okay, thanks, Etienne. Mr. Feng, can you hear me?
Can you hear me?
Yes, I can hear you. So,
okay.
Yes.
For the question about gravity buoyancy battery system, until now, I'm sorry, I don't have that information.
Okay, no, that's fine. I think we'll provide that to you in writing.
Okay.
So the next question is also directed to you.
Sorry, if I can just come in, just explain regarding alternative technologies, like using pump storage in mine shafts, for instance, or using compressed air or hydrogen. I suggest or recommend that South Africa should not spend too much effort on those technologies because they haven't been proven and they're not commercialized. We need to focus on the low-hanging fruit, which are proven, and all we need to do is really implement.
Okay.
Thanks.
So thanks. So Mr. Feng, the next question is directed to you. If you can hear me, I think the first part of it, how much more PSH is planned in China in terms of the energy mix in percentage wise?
Yes.
That's the first part. That's the first part, and then the second part is the question that's being asked by Hagai Stole. He wants to know: does China intend to decommission or retire their thermal generating plants? Those are the two questions. Thank you.
Okay. I have mentioned in my presentation that we have published an important file laying out the developing plan for PSH from 2021 to 2035. Our target by the end of 2025, the installed capacity of PSH should be 62 megakilowatts, and by the end of 2030, the installed capacity of PSH should be over 120 megakilowatts. And by the end of 2035, the installed capacity in operation of PSH should be over 300 megakilovolts. And till now, I have mentioned that for the second question, the proportion of thermal power in China now we have about 49% of the total capacity. And now we are carrying out the job of thermal units flexibility transformation, not just retiring them, but flexibility transformation, which means to lower the output of the unit, which can give out space for the traditional thermal power to the regulation of the power grid. Okay.
Okay. Okay. Thank you. And did you touch on the thermal coal-fired power stations retiring?
Okay, for the thermal unit, we know that for the stable combustion of the small unit, there is a lowest limit for small units. Generally, 60% or 70% of the rated power output. The flexibility transformation means we can lower this output limit to under 50%, thus give out space for thermal power unit to participate in the regulation of the power grid. And we estimated that by the end of 2030, over 50% of all the thermal unit should finish the flexibility transformation.
Yeah. Okay. Thank you. And I think I will just, yeah.
I think an important thing is that China has planned for a lot of expansion in pump storage facilities. By 2030, we're still going to have the same as we've got now, with 2,700 megawatts. And we're already on the low end of penetration of pump storage. We currently at 6%. And if I understood the presentation from Mr. Zifen correctly, China is aiming for 15%. So we have a long way.
The penetration of PSH in our power grid should be around 3 to 4%. Only for PSH.
Okay.
Sorry, okay, I misunderstood.
I think that's clear. No, thanks. In fact, it actually helped because also Mr. Feng came in and he clarified. So on our side, while you are there, Etienne, what do you think would be optimal?
Well, we need. Okay, if we compare ourselves to China, China has a lot of hydropower. We have none. We've got very little. And so because hydropower can mimic pump storage, we will need a greater portion or a greater proportion of pump storage than China. But the key frustration I have is that South Africa is not planning for the rolling out of these pump storage facilities. There's no plans for it, and we're going to be caught with our pants down, much like we've been caught with our pants down with the transmission grid. Because it takes so long to build, we need to start now.
Okay. All right. No, thanks, colleagues. Thanks, panelists. I think I have come to the end of the questions and answers session, and I would like.
Sorry, Chair. Just a short question. We talked about our climate. We have a serious shortage of water as such. And my question is to Etienne. Etienne, what lessons did Steenbras, for example, learn from the time when we're heading for day zero in Cape Town? Is there something that we could take there? I know you said you know, the PSH should not the drought should not be a problem as such, but really from the ground, what did the Steenbras team learn from the drought as Cape Town was heading to day zero? If you just can briefly comment on that, please.
I don't have knowledge or precise knowledge of what happened at Steenbras, but what I presume is that yes, there's evaporative losses from the dams. Yes, there's water that goes down into the groundwater. And what may have happened is Cape Town was in such need for water, was that the water in the dams was used to feed the city. And so maybe that would be an example of, well, having pump storage close to Cape Town was actually a godsend, in that you have a big dam of water which you can use when there's a drought. But I don't have the exact details of what happened at Steenbras.
Thanks, Etienne.
Thanks. Any one of the panelists, any parting shots? Okay.
If I
yeah.
If I can make a plea, is what can we do to put pump storage higher up on South Africa's agenda? Again, I think we're too myopic, we're not thinking long term, but what can we do as an association? So maybe outside the session, people can email the association so that we can get some concrete steps.
Yeah. Now it's I think the energy storage chapter is obviously listening. I can see the members online as well. I can see obviously the chair of the energy storage chapter is here, and we need to have a look at that, and perhaps you can be invited to a more detailed discussion. And because that is what we are here to do as SAIEE, we provide the platform for all these constructive debates and discussions to take place, you know, for the betterment of the profession of electrical engineering. So thanks, colleagues. Then the chair has asked me to introduce the president as well. So we are blessed to have the president to be closing for us today in this session. So Pascal Mutosele is the president of the SAIEE. He has 22 years of experience as an electrical and water utilities engineer. He is a registered electrical engineer, PR-Eng, with the Engineering Council of South Africa. He represents ASSAF in its Federation in African Engineering Organizations membership, where he serves as a chairman of the FAEO Manufacturing Working Group. Mr. President, over to you, and thanks for joining us.
Okay, thank you, Monde. You are hijacking me. I'm just actually an attendee like the rest of the others. Let me try and switch on camera. I didn't expect that I will be asked to speak. Okay, mine, I guess it's a simple one. Then I need to just give thanks to everybody that actually participated in this. First of all, I would like to give my thanks to Madam Devaksha Maharaj, one of the organizers, Dr. Pet Naidu, Etienne Roberts, our speaker there, and also Professor Xifeng, all the way from China. Thank you so much for gracing us and enlightening us with your presentations. I want to thank also the chairperson of the Power and Energy section himself, the Monde Soni. Mings Abrabos, our organizer from the from the Institute. Thank you so much, Minx. Some of the panelists there I see, Unyamboze Babu Mpetwa, thank you so much for indulging us in today's webinar. I wish to actually thank the other organizations that partners with us with delivering on this webinar. This is a very good example of a partnership that works. I can see there we have the SAAE Academy of Engineering and the Academy of Science of South Africa, who are partnering with us on this one. Thank you so much, Power and Energy section, in particular your energy storage chapter, for bringing such international experts to address us and share valuable info around pump storage, hydro, and battery energy storage, and what learnings we can take from there as a country, South Africa. We hope for deeper collaboration and more meaningful relationships and partnerships for the greater benefit of the world's energy storage industry. So I want to just say to all the people that attended the webinar today, there were more than 62 people last I checked. Thank you so much for attending the webinar. And please, those that are not members yet of the SAIEE, please join us for this type of technical engagements. Send an email to eschapter@saiee.org.za. It was there on the screen earlier. It's eschapter@saiee.org.za. And then we will invite you to the next engagements. So with that, I wish you a good day. Thank you, Chair. Thank you.
Thank you. The meeting is now adjourned. Thank you.
Hi, Minx.
Yes, we can.
Hi, great. Sorry about earlier, everyone. Thank you for attending, and thank you, Mr. Motsele, for coming in at short notice and doing my thank you. But I want to thank from the energy storage chapter, a specific thank you to Monde Soni for coming in and assisting us from the power and energy section with the questions. If there's any further questions, you can send them to Minx, and we will have them answered, especially for Mr. Zifeng. Thank you to Mr. Zifeng and Etienne Rubbers for the informative presentations. Etienne, I took note of your questions during your presentation, and Monde, thank you for the challenge. We will take this up as a chapter, and we will look into having an answer or some sort of session set up next month. We are working on our webinar for next month. We'll try and incorporate that into our list of items that we want to address as a chapter. It's a good start, I think, to get some of the creative juices flowing. And a special thank you from my side to Dr. Pat Naidu for putting this forward. The collaboration between the sections or between the chapter and the power and energy section is definitely one that we want to continue working on, and also engaging with the other chapters. I think working in silos does no benefit to anybody. So we will continue to engage with the other chapter chairpersons and see what other webinars we could put together of interest to our attendees. Thank you for holding ground for us when technology got the better of us. I appreciate that. And once again, thank you to all our attendees. Minx will be in touch with your certificate, and any further information can be sent directly to her. From my side, on behalf of the Energy Storage Chapter, I'd like to say thank you to everybody. Thanks. Bye.
Vishka, can the panelists stay on?
It's best to just schedule a meeting, MS Teams meeting, Etienne. No problem.
Okay. Thanks.
Thank you.
Minx, are we done with the recording?
Bye,
Yes.
colleagues.
Okay.
Goodbye.
Bye, everybody.
Thanks. Bye. Bye.